So where we finish off from the break, I've just shown you that you can take second moment of area either from the top or from the bottom. Your answer will be the same. No doubt your centroid distance are different, but this is because where your datum is, okay? If you look at your datum, it's exactly pointing at the same line. Okay, so where we are now in solving this problem, so now we found our centroid, right? We got that. We found our second moment of area. So now we want to look at stresses at a specific distance. Okay. So again, I'm going to copy this whole thing and bring it over. So from the analysis that we have carried out, so we're going to call this the top point as point alpha, and the bottom is beta. Okay. So we are also aware that our centroid, the distance from here to here, from the bottom, is 25 millimeters. We found that out already. Okay. So now, based on our analysis, we know that point alpha will be maximum compression, point beta will be maximum tension, because if you look at the formula, where stress is equal to, or stress X is equal to M, for this case mz over izz multiplied by y, right? And the y is measured from the centroid. Okay, so the distance from here to here and the distance from here to here. Okay, so we know that for beta, y is equal to 25 millimeters. For alpha, y is equal to what? 35 millimeters, yes or no? Right? And based on our analysis, we know that alpha will be under compression because of the tip of the moment arrow, and beta will be tensile because it's at the bottom end of the moment arrow. Okay. So now we want to find stress X of point alpha, and then we are immediately, because we know there's compression, we immediately going to put minus, and then the moment is 1500. The y now, right? The y is 35 millimeters. So this is 0.035. And then the izz is equal to, what do we found? 512.5. Did I start recording? I think I did. Sorry, let me check. Did I start recording? I think I did.
Yeah,
okay.
you did. You did.
Yeah,
I did, right? Yeah. Yeah. Sorry, I my problem is I'm on two computers and one same keyboard running two computers. That's when my problem comes. Let me check, okay? I know you guys told me so. Yep. Thank you. So times 10 to power minus 9. So this will be equal to 1500.35 divided by 5.2.5 power minus 9. So it's equal to minus 102.439 times 10 to the power 6 Pascal. Okay. And stress X beta, right, will be equal to positive. Why positive? Because we know beta is going to be tensile. 1500. The distance now is 0.025 from the centroid, right? Right. So from here to here is 25 millimeters. Divide by 512.5 times 10 to the power 9. So 1500 times 0.025 divided by 512.5 power minus 9 is equal to 73 positive 73.171 times 10 to the power 6 Pascal. Okay. So from here, I'm going to do, I know it's not required in this question. I'm going to sketch. Okay. So we're going to sketch our stress profile. So over here, right? So this is my stress in the x direction. So stress in the x direction. So I'm going to go for minus 120, 100, 80, 60, 40, okay, 20, 40. Oh, not enough. I need to move this. Right, 60 and 80. And then we have a y. So this is our y. So you have 10, 20, 30, 40. So this is in millimeters, megapascal, 10, 20, 30, right? So we know that at 35, we have what? 102. Okay, so 35, 102. So eyeball is somewhere around here. Okay. So this is your minus 102.439. And then this is going at 35. Okay. And then at the other point, you have minus 25 running at 73. Okay, so as I say, I'm eyeballing this. Okay, so down here so this will be 73.171, and this is going at minus 25. So now we can draw a straight line. Okay. Yeah, the eyeball is good now. Okay, so this is how your stress will distribute. And as I mentioned before, at the center is where you have your material, right? So now you start constructing your arrow, compression, and then it's going away is in tension. Okay, so this is in tension. Okay, so if you look at if I were to sketch out our structure quickly, so this is how your structure will look like. Okay, this is just a sketch. Okay, the only thing that's accurate is the vertical direction. Okay, so that's how your structure has been distributed. And as you can see, this is symmetrical because this point and this point, the stresses are the same, right? Right. And this point over here and this point over here, the stresses are the same. So that's what we call symmetrical loading. Okay. So this is a complete question that we go. So imagine if you have a question like this, you can also combine with your what? Shearing stress. Okay. So later on, we'll go into how we combine both of them using Mohs circle. Okay. So that will be later. Right. Anyone, any questions so far, please? Anyone? No? Okay. So the next topic, okay, so this is on sandwich material. Okay, so the next topic And it's not really difficult. It's just there's a concept they have to know. So someone asked me why positive 35 and why negative 35. This is because my y direction is going upwards. Okay, that's why it's positive 35 and 25 because this is minus 25. That's all. Okay, that's the reason why. Okay, I hope. So is this for bending moment? So this is stress x in the x direction due to bending. Okay, due to bending moment. Okay, I hope this answer your question. Anyone, any questions? Are we okay? Right. So the next part